homework, I chose to do question number 2. So let's start with part A. I'll read the question. A battery with electromotive force 9.00 voltage or volt, an internal resistance 1.10 ohms, is in a complete circuit with a resistor of resistance 15.3 ohms. Find the current in the circuit. So I'm gonna start off by drawing my circuit. So, okay. So the battery is 9.00 voltage of the electromotive force. So that's the maximum I guess I can hold. So let's draw the battery. I normally just put lines. I'm gonna put 9.00 voltage, and then it says that it has the internal resistance 1.10 ohms. So we're gonna put that. I'm gonna put it here. Okay, so internal resistance gonna be R 1.10 ohms, and then it says it is in a complete circuit with a resistor of resistance 15.3 ohms. So that's the big R, and I'm gonna put it here. So R 15.3 ohms. And so we're trying to find the current in the circuit. So that's gonna be I. So we're trying to find the current. So to start that, we would have. So let me explain the circuit again one more time. So I drew the battery. The battery is like the source. So inside the battery is the voltage source, which is called the electromotive force or EMF. That's where I put the little Greek letter epsilon there. And then this. So the symbol of that little symbol right here is gonna represent the electromotive force of the battery, and it's normally measured in volts. Then I drew the internal resistance, which is here, 1.10 ohms. So it's so that's basically the internal resistance is represented by the lowercase letter r and is measured in ohms. And then I have the resistor, which is the big R, and that's also measured in ohms. And then now the current, we're gonna draw the current arrow, which is up here. I'm gonna do this way. That's gonna be this way, the current. So this arrow is showing the direction of the current, and the current is represented by the capital letter I. So it basically it represents the flow of the electric charge through the current, and it's gonna be measured in amperes, I believe that's how you say it. And then so around the circuit right here, around it, because there's only like one path for the current to travel, this is called a series circuit. It is a series circuit. The same current flows through, like the same current flows throughout like every component. Okay, so now I'm going to do the calculations. So For the calculations, I'm going to be using the formula that was given in the textbook in the example. So let me draw the formula. Wait a minute. Okay, which is I equals to the Greek letter E over R plus lowercase r. So the I is the current, and then the electromotive it goes up here, and then we have the resistor and then the internal resistance. So this equation comes from the textbook. For a complete circuit contains like a battery with the internal resistance. Since the internal resistance and external resistance are connected in series, I'm gonna first add them together. So let's do that. I'm just gonna draw an area here. So that's gonna give 15.3 ohms plus 1.10 ohms. And that's gonna give me 16.4 ohms. So the total resistance of the circuit is 16.4 ohms. And then I'm going to divide. So the I, we're basically trying to find the I, which is the current, which is set in the question. So the electromotive force is 9.00 voltage. And so I'm gonna form the equation now. So we're trying to find the I, which is the current, and we're gonna put 9.00 voltage, and we're dividing that by 16.4 ohms, and that's gonna give me, let me put in my calculator. Okay, and I got 0.5487804.878. So I'm just going to stop it here, and then I'm gonna round it. So like I said earlier, the give me 1 minute to think. Alright, so like I said earlier, the current is normally measured by amperes, so that is gonna be A here. We're gonna round this to the third decimal point, which is gonna be, let me write it here, which is gonna be I, the current, is equals to 0.54, and we're gonna round it in 9 in amperes. So that's my answer for the first problem. So now we're gonna do part B. Find the potential difference across the resistor. So we have to find the potential difference across the external resistor. So the formula for this would be um I believe it's V. So let's first draw the diagram for. So I'm just gonna copy the diagram from part A, but since it was missing the current, now we know the current and we're just gonna add it. Or we can, yeah, we'll just do that. Or actually, I'm just going to use the same diagram up here. So we're gonna fill that up. So we're gonna put 0.549 amperes. So now we know the current. So now we're trying to find the potential difference across the resistor. So that's gonna be this right here, which we're gonna label it as VR, which is gonna be the potential difference across the resistor. So hold on, give me a minute. So the V is potential difference, basically. The V means potential difference. So let me write that down. VR, so potential difference, and we need to find the resistor. So we're gonna do current times R, the resistor. So that would be so I'm gonna use the Ohm's law, because the voltage across a resistor equals the current multiplied by the resistance. So let's fill in the equation. So we found out the current, which was 0.549, and then R, the resistor, which we know right here, it is 15.3 ohms. So let's put that in the calculator. 0.549 times 15.3, and I got the answer as 8.3997. We're gonna round it. 8.4 would be. And so after we multiplied the current by the resistance, I obtained 8.40 volts. This voltage is only across the external resistors. And so now we're going to do part C. So let me read part C. Okay, so for part C, we're also using the same diagram up in part A. So part C, find the potential difference across the battery terminals. So so now we're going to have to find the terminal voltage of the battery. So we're gonna use this formula. Part C. So we're gonna do V finding the battery terminal. The battery I'm gonna put term for terminal, and we're gonna be using the equation since we have to find the battery terminal across we're trying to find a potential difference across the battery terminal. The potential difference of battery terminal. And so to do that, we would have to use the electromotive force up here, and we're gonna have to subtract it by the current I times the small resistor, since we're trying to find the potential difference across the battery terminal. And so that would be the way we would have to do it. So hold on, let me finish writing I believe I said electromotive force, subtract that by current and the internal resistance. So let's put that together. Oops. Oh. Okay. V battery equals, so we know that it is 9.00 voltage. Subtract that by the I, which is up here, 0.549 ampere, and we're going to multiply it by the internal resistance, which is 1.10 ohms. So we're gonna put that in the calculator. 9.00 minus 0.4549 times 1.10. And I got the answer as 8.3961. We're gonna round it, and we're gonna get 8.40. So so basically, when the current flows through the battery, some of the energy is lost across the battery's internal resistance. But because of that, the terminal voltage is always less than the electric motive force, while the circuit is operating. So that's why I got the answer at 8.40 voltage. Don't forget the V. So if you notice that this is like exact similar number to the voltage across the external resistor. This makes sense because the battery terminals are directly connected to the resistor. So let's do part D. And for part D, this is a separate question, so we would have to make a new diagram. So let me read the question. When an automobile battery with an electromotive force of 12.6 voltage is connected to a resistor of resistance 24.0 ohms, the current in the circuit is 0.450 amperes. Find the potential difference across the resistor. So this would be a little more simpler, since we are given most of the stuff. So let's go ahead and draw the circuit. So it's similar to the circuit that we drew in part A. Okay. So here we're gonna draw the resistor, and we are trying to find the hold on, give me 1 second. Okay, so this is like the series, obviously. We're gonna need to do the big R, the small R, the internal resistor, and the resistor. And the battery, we can add it up here, and the current up here. Yeah, so let's do that. I'm just gonna use a random color. So we know that the the current in the circuit is 0.450, so we're just gonna draw it here. I equals to 0.458 as the cut amperes. Sorry, and then I'm gonna draw the resistor here, which is 24.0 ohms. And we don't know the internal resistance, and we have to draw the this is the battery, I believe. Yes, the battery, which is EMF, which is the electric motive force, which is 12.6 voltage. Oops. I think that's all we have to draw. And so basically this problem gives me an electromotive force of the battery, the resistance, and the resistor. The external resistor of the and the current flowing in the circuit, but we just don't know the small r, and I think that's later on. So we are going so the electric motive force is 12.6 volts, and the external resistance is 24.0 ohms, and the current is 0.450 amperes. So we're gonna use the Ohm's law, which is V equals to I times R. So so this is the we're in part D, right? So the potential difference is going to be the potential difference, and we're multiplying the current and the resistor. So I'm using the Ohm's law because I want the voltage across the resistor, and the Ohm's law states that the voltage across the resistor equals the current multiplied by the resistance. So let's solve that. So we're gonna do the current, which is 450 amperes, and the resistor is right here, 24.0 ohms. Okay, so now let's solve. Let's put in my calculator. 0.450 times 24.0. Okay, so the answer I got is 10.8 volts. So the potential difference across the resistor is 10.8 volts. Oh, let me write that note. Okay, now we're gonna do part E. We're also using the same diagram for part D, so I'm just gonna put it a little bit up. Part E. Okay. Find the internal resistance of the battery. We're doing that question, yes. So now, since we this is going to be really easy because we have mainly everything. So we're gonna use the formula electric motive electric motive force, and we're gonna multiply that. We're trying to find so we're gonna do electric motive, and we're putting V as the potential difference over volts, add that by current times that by the internal. So this is the equation that I remember I saw in the textbook. So the electric motive force of the battery equals the terminal voltage plus the voltage drop across the battery's internal resistance. So we have to find this small r, which is the internal resistance of the battery. So we're gonna take that out, and then we're just gonna bring everything together. Here, so that would be negative, and that would be, oops, minus that by v, and then we're gonna divide the I into the current. So this is our formula. So I rearranged the equation to isolate basically the unknown that we don't know, which is the internal resistance. So let's let me put that up because we're gonna be using that. So the E is 12. The electrometer is 12.6 volts. Subtracting that by the V that we found out here, which is the potential difference. The V is the terminal voltage or the potential difference. So we're gonna put 10.8 V. And then we're going to divide over the I, which is the current, which is 0.450. So let's put that in the calculator. Okay. And so the I got was 4.00. And the internal resistance, I don't know if you remember, but it's ohms. So it's going to be, oops. So that is what that is what R equals to the internal. So we found out this is now actually gonna be 4 ohms. So we found that out. So this result makes physical sense because a battery with the internal resistance loses some of its voltage inside the battery itself. So that's why the terminal voltage is lower than the electric motive force. So now we're gonna be doing is part F, which is a separate problem. So we're gonna have to draw a diagram separately for that one. Part F. Okay. In double A battery has an electric motive force of 1.50 volts. After being used for quite a while, one AA battery had a potential difference across its terminal of 1.30 volts. When it is connected to a light bulb with resistance 20.0 ohms, find the current in the circuit. So let's draw the diagram. Okay, so let me draw that. Okay. So just gonna. Okay. So let's start the battery first. I'm gonna put the battery over here where I normally do. And I'm gonna put the internal resistor here, and I'm thinking of putting the light bulb with resistance here, and then current as I normally put up there. Okay, so this is gonna be the battery, and this is gonna be the internal resistor, and this is gonna be the bulb. I'm actually gonna draw it. Oop. Okay, draw a bulb. Okay, there we go. And this is where I put the current, which we don't know. So let me put this. So we know that the electromotive force is 1.50 volts. And then it's basically used a lot. So we're gonna just put used. And the resistor, the internal resistor, we don't know. And this is gonna be the resistance of 20.0 ohms. That's the light bulb. And since it says that one AA battery has a potential difference across its terminal of 1.30 volts, so I'm just gonna write it here. We're gonna name it VAB 1.30 volts. VAB is basically the potential difference across its terminal, which is 1.30 volts when it's connected to the bulb with the resistance. So we're going to use the equation V equals to 1R, and this is because we are trying to find the current in the circuit. So we're gonna I'm using the Ohm's law because I know the voltage across the resistor and its resistance. So we just need to find the I, which is the current. So to do that, we're gonna have to divide. So the current is equal to the V is up here, so it's 1.30, and we're just gonna divide that by 20.0, the resistor ohms. So I'm gonna put that in the calculator. 1.30 divided by 20, and I got the answer as 0.065, and we're going to we're going to make it amperes. So it's gonna, if I'm putting in scientific notation, 7.50 times 10 to the power negative 2 amperes. So this is gonna be the current in the circuit. So that's the I. So we find out the I. So now we're gonna do is we're going to, let me make this smaller so I can use this diagram for the next question. Okay. Part G. The part G is find the internal resistance of the battery, which is the small r that we put a question mark because we didn't know. And I'm gonna actually take the question mark for the I because we know the current now, 6.50. But I'm going to put it as the decimal. I find it more easier for me. 0.065A. So amperes. This is amperes and this is also amperes. I just converted to scientific notation to match the answer that I had to put in the question. Let me put up here so it's easier for me to look at again. Okay, so we wrote the I up here and we're trying to find the internal resistance of the battery. So to do that, like we did earlier, we would have to use the same battery equation from, I believe, part E, which is let's copy it down right here, this one, which was internal resistance R equals to electromotive force minus the terminal voltage over the current. So let's plug in everything. I equals to, so it's 1.50. We'll minus that by that, which is 1.30. These are volts. I'm gonna put it here. And then over I, the current, which I'm gonna put 0.065. So let's do that. 1.50 minus 1.30 volts. Divide that by 0.065, which gives me the number as 3.0769. We're going to round it 3.08 ohms. So that is what I got for internal resistance. Okay, now we're going to do a another question. This is the final question. So this is part H, right? Yes, H. So let's read the question. The manufacturer of one brand of AAA batteries states that the battery's electric motive force is 1.50 volts. Its internal resistance is 0.160 ohms, and the maximum allowed the current for short times is 2.00 amperes. Find the smallest resistance to which this battery can be connected for short times. So for this question, it's asking the smallest external resistance that can be safely connected for short time, basically. So basically, I'm going to write down everything that was given. So I'm going to draw the small little circuit. So so we know that the maximum allowed current right here is 2.00 amperes. So we're gonna write that up here, the current, where I normally put my current, and then I'm going to put my my electromotive field battery here, and then my small internal resistance, and then I'm going to put my the smallest resistance to which the battery can be connected, which we don't know. So let me draw everything. So this is gonna be my battery, and then this is gonna be the internal. Okay. We know that the maximum is 2.008. I'm gonna put max up here. Okay. And the electric motive field is how much? 1.50 volts. And the internal resistance is, let me zoom in a little bit, 0.160 ohms. And so the maximum allowed the smallest resistance, so we're gonna put our minimum, basically. Oops, I'm just gonna put minimum. Okay, and we don't know that, so that's what we are looking for, and that's gonna be in ohms, obviously, because it's the resistance. Okay, so we are given all these, and so we're basically finding the the big R, if you can say it like that. So let me form a. So what we normally use is the formula that was in the textbook, which was and the current is equal to the electric motive force, divide that by this the internal. Okay, so I'm going to rearrange this equation. So I'm going to isolate the external resistance, which is the big R. So let's take the R out, which is going to give us it's going to give us electric force, divide that by the current, and subtract that by the internal R. So now I'm going to substitute the known values that we know. R equals to, so the electric motive force is 1.50 volts. We're going to divide that by the current, which is 2.00, the maximum amperes, I believe, right? Yes, amperes. And we'll subtract that by the internal resistance, 0.160 ohms. So we're gonna put that in the calculator actually. 1.50 volts divided by 2.00 amperes, and we're gonna subtract that by 0.60. Okay, and I got the answer of 0.590, and it's gonna be ohms because it's a resistance. So using a smaller resistor would like allow more than 2 amperes to flow, which could damage the battery. So we're going to circle that. So now we're gonna do part I, which is find the potential difference across the battery terminals when it is so connected. So this is similar to what we did before. So basically it's asking the battery's terminal voltage when it's connected to the minimum resistance that I just calculated. Oh, I forgot to put that. I'm just gonna put okay. So we found out the minimum up here. So now we can. I'm going to and I can. Min is 0.590 ohms. There we go. Okay. So now we're finding the potential difference across the battery terminals. So we did this previously in one of the parts, I believe. So what we're gonna do is we're gonna use the equation V equals to IR, since we know the current and the resistance, and this would be the best way to find obviously the potential difference, which is V. So I'm going to put I. Okay, so the potential difference is going to be equals to current times the minimum. So we know that the current is 2.00 amperes. Multiplying that by the R minimum, which is 0.590 ohms, and we're going to put that in the calculator, and I got 1.18, and V is equal to 1.18, and it's gonna be volts. And also So basically, the battery that had the electric motive force of 1.50 volts, and the terminal voltage is lower because the part of the voltage is lost across the battery's internal resistance. So let me circle that. So throughout this problem, I used like the three main equations from the textbook, which was the Ohm's law. The second equation was the current in a complete circuit containing the battery with the internal resistor, and then the third equation I used was the battery's electric motive force to its terminal voltage and its internal resistance. So this is question number 2.